Welcome to the office. We want to continue talking about rectangular coordinates, 3 dimensions here, and we're going to look at distances in 3 dimensions. So distances in 3 dimensions is very similar to distances in 2 dimensions, of course. Not too much of a surprise there. But if we are working in our 3 dimensional coordinate system, get this kind of drawn out here, X, Y, Z. This just gives us an orientation so we know where we're at. But let's say that I've got 2 points in space somewhere. They happen to look like this. Okay. If I want to, I can recognize that I have to move some distance in the X, Y, and Z directions. So what I'm going to do is I'm going to recognize that maybe I have to move this far in the X direction, sorry, in the Y direction, this far in the X direction, right? This is parallel with Y, this is parallel with X, and then let's see here, I'd end up moving in the Z direction as well. So I have some change in Y, some change in X, and some change in Z. So there's 3 changes here in our 2 dimensional coordinate system, X and Y. Of course, we only ever had 2 changes. We had to move over and we had to move up. Here we have to move over on our plane and then up in our Z direction. So when we had a change in X and a change in Y, right, essentially we're using Pythagorean theorem to get a distance formula here. And we'll use the same thing in our 3 dimensional coordinate system. So I think this is kind of fun. Maybe it's not the most exciting development, but it's pretty straightforward anyway. If I want to find the distance, let's see here, I guess let's put that in blue as well. What I want to find is this straight line distance from P1 to P2, whatever those 2 points are. If I want to find that straight line distance, I can start by recognizing that maybe I could use this length here and this length here, right, to have a right triangle. But this one I can determine as the hypotenuse length of this right triangle. So this distance here, actually, let's label it this way. There we go. This distance here is the square root of the change in y squared plus the change in x squared. And then this side length here, of course, is just the change in z. But that allows us to observe that this distance here is the hypotenuse of this right triangle. So the distance of this side length would be this side length squared, square root of delta y squared plus delta x squared, right? This side length squared plus this side length squared. And taking the square root of that sum. So once we have that, easy simplification, right? Square root and square cancel out. So this is just the square root of the change in y squared plus the change in x squared plus the change in z squared. So it actually looks exactly like the distance formula in 2 dimensions, which would have been just the square root of the change in x squared plus the change in y squared. Right? These look the same. You're just adding that additional dimension, right, z. So what we get for a distance formula, just to formalize it a little bit. So for P1 being x1, y1, z1, and P2 being x2, y2, z2. Okay, so we have 0.1 and 0.2. We have the distance between those two. So oftentimes distance is just given by the letter D. We can also have distance between P1 and P2. In the text, some textbooks give it as absolute value P1, P2, right? So these are all notations for distance. And the computation itself is given as, right, how do we find the change? We just say x2 minus x1. x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. There we are. And so that gives us a distance formula. Okay, nothing too surprising there. So if we return back to our problem, what we get is a distance of, I just got to review our points here. So 1, 2, -1, and 2, 4, 6. All right, so difference in x values, 1 minus 2. Sure. Well, if we do it the other way, then it gives us positive. So let's do that. We'll do 2 minus 1, 2 minus 1 squared plus 4 minus 2 squared plus 6 minus a -1 squared. So we've successfully plugged our values into the formula. That's wonderful. Oops. We've successfully plugged our values into the formula. We should simplify. 2 minus 1 is 1. 4 minus 2 is 2. 6 minus a -1 is 7. So I can evaluate each of those. This step here, maybe you don't need, and that would be okay. But we have 1 plus 4 plus 49. This gives us the square root of 54. Now, if you're an engineering student, I find oftentimes that such folks like to punch that into their calculator and find a decimal approximation. I'm not a big fan of that, right? I like to work with exact values. It looks a lot nicer. So in your applications courses or in applications here, maybe we can use decimal approximations, but I really like the exact value. And actually, that's not quite done yet either. We should recognize that this is 27 times 2, so we can actually recognize it as 2 times 3 cubed. And we know the square root of 9, so we can write this as square root of 9 is 3 times the square root of 2 times 3, or simply 6. And that's actually the answer that we would like to give in a simplified form. If you were to end here, that would definitely be pretty good. Not a big deal if you don't simplify, but not necessarily full credit when it comes to exams and that sort of thing. Not that it's going to ruin you not to simplify, other than there might be simplifications in larger problems that that make things work out very nicely. If you overlook those can be a problem. All right. Thank you for your time. We'll take a look at some more examples in 3 dimensions in our following videos. See you shortly.